slope stability in open pit limestone quarry. So I've been adequately introduced, so let's just go straight to today's business. So my research work, my presentation today is organized into these 7 chapters. So moving on to chapter 1, an introduction. And in the first case, I'd like to introduce Kenya's mining industry. Here we have maps of Kenya showing the various mineral resources we have. And on this side, representing the various economic sectors that contribute to Kenya's GDP. So in Kenya, we have discovered over 970 mineral resources. There are those old ones that have been mined for long, like trona, gold, and diatomite, and others also have ceased operations like copper, garnet, and graphite due to market dynamics. We have other resources like coal, iron ore, limestone, manganese, gypsum, natural carbon dioxide, and titanium, which are actively being mined. And our energy resources also are like we have petroleum, natural gas, and geothermal resources, which also has both some other colleagues here. Generally, our mining industry is still at nascent stages and contributes just about 0.7% to the national GDP against a potential of between 4 to 10%. Here, this photo is of some rubies. It's our lab's tradition to display minerals in our country. So my favorite color here is of the purple ruby. Yeah, right. On to limestone quarrying. Quarrying generally is open pit mining where the rock itself is the target substance, and there's little waste created in this case. We have hillside, hilltop, valley bottom, and coastal type quarries. And from mining limestone, we have we get products from the rock itself, such as dimension stones for construction, pavers and wall tiles. We have landscaping equipment. We get aggregates and also additives to industrial products such as fertilizers, pharmaceuticals, paint, cement production, and also breakfast cereals. And from the carbonate rock formations, we get water aquifers, we get oil and gas deposits. We could also have ores of bauxite, manganese, coal, lead, zinc, gold, and iron ore. Now on to karst formation processes. Karst forms about 20% of Earth's continental ice-free mass, and some of the most fragile and susceptible environment on the Earth's surface. Karst forms on evaporite and carbonate rocks, and for karst to form, there needs to be over 70% of calcium carbonate content. The karst terrains form when the excavating effects of water override mechanical erosion. And in a karst landscape, we have the exokarst on the surface, epikarst just below the surface, and endokarst way deeper in the Earth's crust. There are a number of safety issues that are inherent in a karst terrain, and their formation depends on the geological structure and also the rock strength. We could have cave collapse, like in this bedded rock mass here. We could have sinkholes in a fractured rock mass. There could be sinkhole risks also due to underlying caves, and we could have a cave developing, like in this progression here, cave evolving into a slope collapse, and also rocky pinnacles in stronger karst rock that also pose a risk to infrastructure like roads. So to the problem statement, while we find ourselves with this research, First of all, the rock mass under this study is a loosely cemented rock mass with the numerous karst cavities and an indefinite spatial distribution. And the current slope design at the quarry is also of concern because mining is carried out with vertical benches and some instabilities have been reported in the quarry. There's also the proximity to the Indian Ocean, which is a concern for the safety of mining, and also human settlements around the quarry land, also an issue of concern because we need to ensure the humans are not affected by the excavation activities. Also, there's a challenge of modeling these the karst features when doing slope design so as to cater for them in the slope design. So the final goal of coming up with an appropriate slope design based on the rock mass behavior, this study has 4 objectives. The first one is to determine the rock's physico-mechanical properties through laboratory tests and evaluate the rock mass using a suitable classification method for carbonate rock mass, and also to assess the stability condition of the Congo quarry slopes and come up with a means of modeling and incorporating the karst rock structure into the geotechnical model. The third objective was to to evaluate significant factors impacting stability of slopes in weak rock. Excuse me. The fourth objective is to determine the optimum heat slope design for safe excavation and recommend measures for maintaining the integrity of quarry slopes. Is motivated to do this work as a result of the existing gaps in modeling rock mass structural defects, and especially in weak karst rock masses where there's high textural porosity and a complex geological structure that's not easy to model. And the current numerical modeling and analysis software can conveniently model joint networks, but karst features are not well represented. Then there is also a rehabilitation plan for the quarry that recommends vegetation. There's clear plan on revegetation, but there's not much for slope management, so I got the motivation to make a contribution towards this. And finally, the quarry land will be used as a nature trail, though at the moment it's actually accessible to the public. So it's very important to ensure that to eliminate any geohazards involving humans operating on the quarry land. So this is the flow of the work from field investigation to laboratory tests to rock mass classification, then numerical modeling, and finally to slope design and measures for maintaining slope stability together with guidelines for mining near a large water body. On chapter 2 is an introduction of the study area. Single quarry itself here at the south coast of Kenya in Kilifi County, and Kenya is in east of Africa with the geographical coordinates given here, the latitudes and longitudes given. And the quarry land here lies parallel to the Indian Ocean. It measures about 4 kilometers long and 2 kilometers wide, and a relatively flat-lying deposit that goes up to 70 meters deep. Now, on Kenya's coastal belt is divided into 3 physiographic units: the coastal range, foot plateau, and the coastal plain. And we have the single quarry on the coastal plain here, where elevations are mostly less than 33 meters above sea level. And it's mostly made up of Pleistocene sediments. To the geology of the deposit, two primary geological units, that is coral reefs and coral sands, make up the geology of the area. And the sandbars are erratic and oriented parallel to the beach line. There's high textural porosities with density values ranging from 0.5 to 1.5 grams per cubic centimeter. And the carbonate content is up to 95%. There's also entrapped silica, which increases variability of the limestone grade. On the right side, we have stratigraphic sections of the stratigraphic sections from the quarry, showing various the materials making up the deposit here, from topsoil to high-grade limestone, low-grade limestone, and karst. And the hydrogeology is majorly controlled by the two geological units, the sands and the coral limestone, which are highly porous and permeable and lead to high aquifer transmissivity. The groundwater table dips gently to the ocean, and all the water discharges into the ocean. Rainwater also drains into the ocean. And the area experiences semi-diurnal tides, that is two high and two low tides of approximately equal side each lunar day. And during high tide, pools of water can be seen on the quarry floor as such. The quarry is excavating limestone for cement production, and the proven reserves are at 72 million tons above sea level, with an annual production of 1.7 million tons. The stripping ratio is at 1 cubic meter to 4.5 tons, and for a 5-year plan, the stripping ratio is at 1 cubic meter to 21 tons. The final pit is expected to be a 20-meter platform with a 40% inclination grade, and the quarry operations include stripping, drilling and blasting, loading and hauling to the plant, there's the mineral processing, then there is quarry safety management and environmental management. So specifically at the quarry, the following geohazards and instabilities have been reported. There's been bench undercutting as a result of a sandy soft layer underlaying a hard overhanging layer, and this poses a risk of the upper hard layer falling over, and there's planar failure that has been reported before. Also bench collapse as a result of an underlying cave collapsing. There's been a rock fall after blasting, where a rock block breaks away from the main bench. Also toppling failure has been reported, and also hazards from the existence of such voids and cavities on the slope faces, also sinkhole on the bench, and other small-sized cast hollows on the slope faces as such, which also compromise on the rock strength. So, as a result of due to the presence of those geohazards, we could see that stability analysis and also space design, going by using the numerical analysis, modeling and analysis tools. With the slope safety analysis as shown here, from this model to the stress analysis result here, we could see that we can determine the slope safety factor and also a shear plane here. defining probable circular failure. We could get the deformation vectors, but we cannot make an inference of instabilities as a result of the cast features that we've mentioned before. We cannot make inference of those instabilities. So the small-sized cast hollows cannot be ignored as they are not represented in this model, and also because of their indefinite spatial distribution, the softwares have not been able to accommodate them. So what we need is a robust geotechnical model with an ideal rock mass model, so that we can have a reliable stability analysis and a design solution. So in summary of chapter 2, we are dealing here with a coral limestone of Pleistocene age with high carbonate content up to 95% and active calcification, and the geohazards are directly linked to the karst features. Numerical modeling so far cannot accurately represent the rock mass, therefore we cannot have much confidence in the accuracy of the slope stability analysis and slope design. Next, let's look at the rock mass of single quarry under the following subheadings. So here's the composition of the rock mass from X-ray fluorescence analysis, showing the various chemicals making up the rock mass, and here the grading of the limestone based on the percentage of lime. That is how they do it for the cement production. So here here's a presentation of the laboratory tests that were carried out to determine rock properties. So from the field sample research to coring, these are tests that were done here at the rock engineering lab, and cutting the samples to shape, then saturation for porosity test, and oven drying after saturation, then the uniaxial compression strength test. These are the samples before UCS and after UCS, and the indirect UCS test to determine tensile strength, and these are the samples after indirect UCS test. The results are tabulated here for the intact rock properties, and from the lab test we categorize we classify the rock under ISRM is an International Society of Rock Mechanics scale, which classifies rocks based on the uniaxial compressive strength. So the rock falls here under the weak category, where the UCS is less than 25 megapascals, and when saturated, the strength moves to even the weak, very weak section. So our rock is mostly in this section. We're dealing with the weak rock. These graphs present the variation of rock properties with porosity, and due to the limited number of data points, we could not generate clear graphs, but we can see a clear trend of degradation of rock properties with increasing porosity. And let's look at the stress strain behavior of the rock. For this case, let's look at this first graph, the one in green, where we have three sections, A, B, and C. From section A, there is the increasing strain with no increase in stress, and that is the part of pore closure. Section B is linear, with, where we have elastic deformation until there is failure at the peak point, and then brittle failure at this point. Thereafter, there is a reduction in strength to almost zero. So we have plastic failure here, a case of strain softening. So generally, the rock behavior is described as elastic brittle plastic. behavior. Now, to classify this rock mass, we do classification to identify and collect rock. We do classification to identify and collect rock mass features, so as to facilitate seamless communication between engineers and geologists regarding quantification of rock mass quality. So with this rock mass, we have there have been some calls, but the recovery was quite poor. And right from what we've seen before, the formation of karst, we could see also traces of soil that are washed down due to seepage. We could see karst caves, and even in the background there, we could see some karst caves. So with the weak rock, with the nature of this rock mass and the poor recovery, we find that the rock mass classification systems of RMR and Q system are not quite sufficient. So GSI method is proposed to use in the classification of this rock mass. So GSI is the geological strength index, and also, as much as it has been used for long, still its usage has not quite accommodated carbonate rock masses which are prone to calcification. So there's the GSI method for porous carbonate rock masses, ones without large caverns, that makes use of rock quality and state of calcification to classify the rock. So in this case, we look at the rock mass structure, that is the blockiness, and also surface condition of the discontinuities, and the values of UCS and rock porosity that are also considered. Here we have two tables, the one on the left for rock mass without bedding, and on the right is for rock mass, for a bedded carbonate rock mass. So here is a presentation of rock quality of rock in various sections of the quarry. So I picked out 8 sections for analysis. So for each section, there was the evaluation of the blockiness, or how cemented the rock mass is, then considering the UCS, the uniaxial compressive strength, and the porosity to get the GSI value. And those are tabulated here, where we give the class, the GSI value, and the porosity as such. So after getting the GSI value and with the value of porosity, we classify them in this table. So the rock mass we're dealing with falls under class C4, D4, and the D5, where the rock mass is described as soluble. For class C4, the rock mass is quite soluble, that is C4 and D4. Soluble rock mass, over 50% can be dissolved and also to form residue. And in class D5, where the porosity is higher, there's also the carbonate rock getting decomposed to form the red soil, some of which we've seen getting washed down into the lower sections of the slope peaks. So generally, on the GSI chart for carbonate rock without beddings and foliations, we find our rock mass falling under this category, from the blocky or disturbed to the disintegrated, poorly cemented rock mass. So this is the rock quality we are dealing with. And we have seen the failure, like the stress strain behavior of our rock as elastic, brittle plastic behavior. So just comparing the Hook-Brown criterion, the nonlinear criterion, which represent elastic, brittle plastic behavior, comparing with Moore-Coulomb's elastic plastic behavior. So in this case, we see that rock mass is best modeled using the Hawke-Brown criterion. And to obtain the rock mass properties, the Hawke-Brown criterion makes use of the laboratory test, the intact rock properties, together with the GSI value that has been determined that quantifies the rock mass strength. So in this case, we are able to get quantities that we can use for slope analysis and also slope design. So in summary of chapter 3, we are dealing with a weak rock mass as has been classified based on the ISRM scale, a rock with elastic brittle plastic behavior that is best modeled with the Hawke-Brown criterion. And the rock quality in terms of GSI is between 14 to 30, and also it's classified under classes C4, D4, and D5. And the rock mass quality is described as a blocky or disturbed to disintegrated and sheared, where we have the carbonate rock getting decomposed to form some red soil, also known as terra rossa. So having described our rock mass, let's look at numerical modeling of karst. Numerical modeling so far for slope stability, we have these methods of continuum, discontinuum, and hybrid methods. In this study, continuum modeling is used, finite element continuum modeling, using the software RS2 from Rock Science. The finite element method in this case uses shear strength reduction principle, where the cohesion and friction angle parameters are reduced by a strength reduction factor given as SRF until safety factor is obtained. The safety factor is equivalent to the safety factor of the slope under study will be equivalent to the critical strength reduction factor of the model. And also we will use the shear strength reduction area to determine the stability condition at a point. The FEM method in this case will start by creating a model, developing a mesh, and setting boundary conditions so that before we do the analysis. And also the RS2 software's seepage analysis module is also made use of for groundwater analysis in this study. Interpretation of results from RS2 is based on records of displacements and velocities, where increasing displacements and velocities indicate instability, and steady displacements and decreasing velocities indicate stable conditions. Also, instabilities are indicated by constant velocity vectors, organized velocity fields as such, and plasticity fields also indicators of instability when interpreting the results. So to the status of modeling of karst, I just put this is grain-based modeling of samples of karst rock. So far using DEM, discrete element method, but just a sample scale. We've also had CT scanning and digital image processing, which has been used for, this was a rock and soil mixture on a slope. There's also been a stochastic model developed from drill cores with the size range from 0.2 to 200 meters. And this one was done on strong rock, where there was a large number of core drills that was used. So far with the current status of modeling, we've seen just possibility of doing up to sample scale, say for DEM, and also the tedious process of digital image processing. Also, a large number of drill cores required to to model this, which is not quite applicable to a case where we have poor recovery from in weak rock. So in this study, equivalent porous medium (EPM) is used to model the cast. And the EPM principle is such that when we have a slope face like this with cast hollows as such, and some of them forming features as indicated by the dotted lines, we can have a sketch of the cast hollows as such, and the EPM principle reduces this to just to use circular cross sections. One can use many other cross sections, but in this case, we're using circular cross section to represent the area occupied by these cast hollows. So that's the method used to model cast in this study. To obtain the cast data for analysis in this case and to develop the equivalent porous media, we would have the slope section, an area of the slope, and identify the cast hollows that are there, the sizes and the number that fall within a specific size. So we would represent the area occupied with we represent the area occupied by the cast hollows against their sizes, in this case in the radius. So the measurement would be as such. We will have a slope face, and then, for instance, just as indicated, we have the cast hollow here, but we take an equivalent circle. In this case, we take the diameter to represent the cast hollow. So in this, with the number of cast hollows indicated, the value we would be picking from here is the holes density given as D, which is a ratio of the total area of cast hollows to the area of surface under consideration. So we will have an input parameter of cast hollows D to use in our subsequent analysis. And the assumption made when collecting this data in the EPM method is that we've already accounted for larger cast hollows through cast mapping. And also, we assume there's no filling in the voids, and the shape is inconsequential in this case. We just take care of the area occupied by the cast voids. So generating the equivalent porous medium was done using MATLAB's random number generator using the bubble bath function, and the input parameters are the holes density, as I've mentioned before, and the hollow sizes. From there, we end up with a DXF file output, which is imported now to the RS2 model, so that we have our geotechnical model with all the structural features represented. In summary, we see that the capabilities of RS2 to model complex geometry makes it suitable for this analysis, and also the seepage analysis module enables us to have a proper analysis towards to achieve the objectives of this work. With the cast are modeled using EPM, the equivalent porous medium, with a circular cross section, and the area of the surface occupied by the cast is the main point of focus, not the shapes in this case. So let's look at the significant factors that impact stability of slopes in weak rock. First, I would like to give some 3 case histories of instabilities that have been reported in weak rock, such as Lagendorf chalk mine in Germany that experienced lots of vein scale failures. Also, Rio Tinto's boron mine in Los Angeles also had slope sensitive to changes in pore pressure, the geological structure orientation, and their discontinuity and their continuity. Then Talagon mines one in Philippines also experienced some instabilities. There were tension cracks and multiple bench failures after heavy rainfall. And in this case, it was noted that geological structures did not play the main role, and the instabilities were attributed to the rock strength, to the low rock strength. Therefore, rock strength was playing a major role in controlling the stabilities of these slopes. The slopes would therefore remain stable provided that the rock mass shear strength is greater than the total stress. And the rock mass instability would therefore be instigated by shear strength reduction and total stress increase. So shear strength reduction occurs when we have an increase in pore pressure, and total stress would increase when, as a result of loading on the slope, and also when we have water in the pores of the slope, we have an increase in the total stress. So how about the structural defects that we've looked at, the cast defects? So that's, we'll be looking at how they contribute to, we'll look at their impact on slope stability next. So next is a parametric analysis of the factors we are considering to impact on slope stability. We look at the pore pressures, which the sources of pore pressure in this case are groundwater, rainwater, and the ocean water tides. And then these are the rock mass properties used for the analysis. This is the slope model for the parametric analysis. The slope model here and its safety factor of 1.13 gives us the reference point. So the results of the parametric analysis will be analyzed against this safety factor here. So the impact of groundwater here was modeled as a total head with 1 meter buffer zone below the quarry floor. So we see it was modeled with an excavation of 20 meters, at an excavation of 30 meters, at 40 meter excavation, and also 50 meter excavation. So we could see that at 20 meter excavation depth, there's really no change in the safety factor, but below 30 meters, at 30 meter excavation depth, that is below the groundwater table, there's significant reduction in strength. And to the impact of rainfall, we could see at 20 meter depth and 30 meter depth, there's no significant strength reduction, but at 40 and 50 meters, there's the strength reduction, and this could be attributed to a large, we could be attributed to having a large slope section exposed to pore pressure. So we end up with higher positive pressures within the slope than in the case where we have a smaller slope. To the impact of the ocean water was modeled at 50 meters from the shoreline, and also at 100 meters from the shoreline. And in this case, we see at 20 meters and 30 meters excavation depth, there isn't much change in the safety factor. But from 40 meter excavation depth and 50 meters, there is some significant reduction in the strength, and that's as a result of a large section of the slope exposed to positive pore pressures. At 100 meters from the shoreline, we see from the impact of the ocean water then decreases as we move far away from the shoreline, but also the impact increases with increasing excavation depth. A combination of the three sources of pour pressure into the model, we see a significant loss of strength, especially from 30 meters of excavation up to 50 meters. Now let's look at the impact of the cast hollows. In this case, the cast hollows were grouped into 4 based on their size, and in this case, the cast matrix, these are the output from MATLAB, where we have increasing hole density going down, and in this case, increasing hole size from the smallest hollows to the largest on this right side. So these matrices are used to evaluate the impact of cast hollow sizes and densities. So set A is the smallest, the one with the smallest hollows. B is all the hollows combined. Set C is slightly larger, and on set D we have 1 meter diameter hollows. So we can see just a general reduction in strength for set A and B. For set C, there is no reduction in strength, and for D, there is a reduction in strength, and this is attributed to having the cast hollows close to the surface. Over here, we don't have the hollows next to the slope face. With an increasing hole density, still we observe just a general strength reduction for the smallest of hollows, that is set A and B. For set C, there is a significant reduction in strength, and also for set D. And with a 1% cast hollows density, still we just see a general strength reduction for set A and B, but we can record more shear planes in this case. And for set D, C and D, also there is the general strength reduction. For set D, with a higher cast hollows density, we could see safety factor is higher compared to when the hollows density is 0.5, and that is because in this case we don't have the hollows so close to the slope face. In summary of the factors that affect stability in the weak rock, we see the rock strength, the pore pressure, and cast hollow defects. They significantly impact on the slope stability, and strength reduction due to cast depends largely on the hollow sizes and density. Small sized hollows up to 0.5 meters diameter, they cause a general strength reduction due to reduction in load bearing capacity of the slopes. And for the larger hollows of 0.5 to 1 meter, their impact depends on proximity to the slope face. Rainfall causes significant strength reduction, whereas groundwater reduces slope stability when excavation goes below the water table, and that's the same case for ocean tides. So for ocean tides, their impact is felt from 10 meters below sea level. Therefore, we can say that excavating below groundwater and sea level will have to incorporate measures to control water inrush into the quarry, into the slopes. Sorry. Now to chapter 6. In chapter 6, let's look at the stability condition of the Pingo quarry slope. 3 geotechnical units are selected for analysis. That is the northern section, the central, and the southern section. The northern section is considered slightly competent in this weak rock range. The central section has a layer of soil on top, and then in the southern section there is a coral sand layer underneath the soil. The slope model in this case was modeled up to the 20 meters depth, and the overall slope angle is at 59 degrees. the benches are here 7 meters, but the top one is at 6 meters, and these are the properties that are being used for stability analysis. The model therefore is as given here. The boundary conditions are in the x. The sides are restrained in the x direction by vertical rollers, and the bottom section is fixed, not allowed to move. The top sections are free. And the mesh used here is 3 noded triangles for simplicity of solution. And we're using 200 mesh elements. That was after an analysis where we saw a constant safety factor from 200 mesh elements. Then the 3 seepage conditions are also considered in the analysis going forward. Groundwater modeled as total head. The adjacent ocean tides also modeled as total head and as ponded load. Then rainfall is modeled as vertical infiltration. The results are interpreted based on the safety factor and the plastic shear strain, which defines a failure plane. Then the yielded elements, which yield in either shear or tension, and the failure trajectories, which indicate potential failure planes. And the acceptance criteria for safety is a safety factor of 1.2. So this is now the slope model used for Pingo quarry. The northern section, central section with a topsoil layer, the southern section that has a coral sand layer underneath, and these the dark areas, those are the cast hollows included. So the safety factors given calculated for dry slope are all below 0.1, as we can see. This northern section is more competent, and with the seepage boundary conditions included, we have even further strength reduction in this case. And as we've seen, the safety factor in the model, that indicates just the lowest value that was calculated in the model, but it's important to get to know where exactly the most unstable section is. So that's why I used the shear strength search area to check the condition of the individual benches. And you can see that the lowest safety factors, yes, they occur on the benches. So we have to be concerned about the condition of the benches so as for us to be sure of the overall stability of the slope. And to vary, in this case, I was varying the geological strength index so as to see how much the slope stability is impacted by the rock strength. So from a GSI of 14 to 28, 40, and 50, you could see a very low safety factor with a GSI of 14. At 28, there was the safety factor of 0.89, and at 40, with a GSI of 40, then there was an increase in safety factor compared to the original condition of the slope. And with a GSI of 50, we see the safety factor has even gone above the allowable, the acceptance criteria. So in this case, I made the conclusion that with the GSI of 40 upwards, then these small size cast hollows don't really impact on the slope stability and might not actually need to be modeled when dealing with the strong rock. Now let's try to identify some failure modes that we could pick out from the analysis results, because we saw the instabilities that are there in the quarry, and it's important to be able to tell what led to which kind of failure. So with the cast hollows, categorized as set A, B, C, and D. So they're all analyzed here, where we are looking at the shear strains, we're looking at the yielded elements and the stress trajectories to determine which failure modes are probable. So for the smallest set of cast hollows, that is A, we see a shear plane on the bottommost bench, and there is more yielding actually on the bottommost bench and the slope toes. And the stress trajectories give an illusion of, they give an impression of a planar failure patterns. So in this case, I made the conclusion that the small cast hollows are likely to cause planar failures. In set B as well, we could see the plasticity mostly on the bottom of the bench and the toe of the bench, and the failure, the stress trajectories also give the impression of planar failures. So in this case, set A and B give the impression of planar failures. Set C, that had the larger hollows, in this case, we see plasticity just concentrated around the cast hollows, and also when they are close to the slope face as such, then we see shear planes developing. And the failure trajectories, in this case, we cannot have definite failure trajectories in this case, unless where now we have a higher density, then there's a probable path of failure. But in this case, we could say that the subsidence or bench collapse will be localized around these hollows, especially when they are close to the slope face. And with the largest hollows of 1 meter diameter, still we can see just the cast hollows. We could see failure concentrated around the cast hollows, and when they are close to the bench faces, then we see a likelihood of subsidence or bench collapse. So therefore we can say that from set A and B, we are likely to have planar failure as seen here, and also when we have the plasticity, when we have the shear strain parts intersecting like this, then there's a likelihood of rocks falling off there's a likelihood of a rock fall. And in this case where we had subsidence, we would attribute it to the occurrence of a slightly larger cast hollow underneath and close to the bench face. So we have seen that the slopes as currently designed are not quite stable, and the lowest shift factor occurs on the benches, with the stresses concentrated on the slope toes and shear planes developing on the bottommost bench. Tensile and shear failures are also concentrated around the cast hollows, where they join up and form the failure parts. And the small size cast hollows don't affect stability when the G side is over 40. We have planar failure when we are dealing with smaller hollows of less than 5 meter diameter, and we're likely to have subsidence or bench collapse when we have sizes from 0.5 to 1 meter diameter. So in this case, we have to work towards optimizing our quarry slopes. So in chapter 7, the final chapter, we're looking at optimum slope design. This is the design process for slopes in weak rock, where from the geotechnical model we determine the slope stability and the instability modes, and then we go to determine the overall slope angle which is dependent on the allowable safety factor, and then the slope configuration, the bench configuration, therefore fitted into the overall slope angle that has been determined. The allowable The overall slope angle is dependent on the allowable safety factor, which is, in this case, we have 1.2 for quarry operations, and for long-term stability, we have 1.3. This table here just indicates some designs of some configurations of benches in other weak rock mines in other locations. So here is an optimization of the overall slope angle, which is done by gradually reducing the overall slope angle and then we determine the one that corresponds to the safety factor that we have set. So for operations where we have safety factor of 1.2, these are the overall slope angles for the north, central, and south region. And for long-term stability, these are the angles we have corresponding to safety factor of 1.3. Now we need to have the bench geometry that fits into the determined overall slope angle. And first of all, the bench height could be determined from these three methods: Psychovic equation, or based on the workplace safety, or also on the efficiency of the workplace. And in this study, the safety of the workplace is considered, where the bench height is limited to less than 1.5 of the excavator's digging height. Then for each overall slope angle, the bench faces are optimized for bench heights of 5 meters, 7 meters, and 10 meters. So in this table, we have bench width and bench face angles for 7 meter bench height. In this case, for 5 meters bench height this side, and on the right side for 10 meters bench height. And for each case, to determine the optimum bench face angle, a safety factor of 1.1 was considered. That is the allowable safety factor for bench scale. So therefore, in this table, I tabulated for each overall slope angle, I have the bench face angle and the corresponding bench width. For the 5 meter, 7 meter, and 10 meter bench heights. Then in each of these cases, we see that the 10 meter bench height gives the most practical bench width. So in this case, I suggest the use of 10 meter bench heights for excavation. Now, after determining our optimum bench design, it's important, since we are dealing with a weak rock that is very sensitive to factors that reduce the shear strength, it's important to apply measures for slope stabilization. And stabilization in this case is targeted towards increasing the shear strength and eliminating pore pressures. And the stabilization measures consider that we are dealing with a loosely cemented rock mass that is undergoing active calcification. Also, we consider the scale of the project and suggesting climate-friendly solutions. So in this case, I was proposing the use stabilization of the slope using vegetation roots. And in this case, this is a formula that represents how the vegetation improves the shear strength of a slope material. So in these two measures of slope stabilization, that is increasing shear strength and eliminating pore pressure, first of all, increasing the shear strength, in this case using vegetation, I was suggesting the use of this specific plant, the vetiver grass, which has 75 megapascal of tensile strength. It's a geotropic fibrous root that grows up beyond 5 meters of length. And besides slope stabilization, it would also help in reducing runoff's erosive energy and also sediment trapping, as illustrated in this sketch here. And to eliminate pore pressures on the slope, first of all, just an illustration of what the vetiver roots look like. They could be planted on very steep slopes as such and still grow vertically downwards. You could see their height in relation to human height, and they grow much longer than that. Also, you can see a section that remained intact after erosion because of the presence of the roots. So, for controlling water on the slope, I'm suggesting the use of geofabrics to protect the slopes from impoundment by rainwater, and therefore to minimize slope degradation. And they could also be combined with the vetiver grass, so we would achieve slope stabilization and also eliminating poor pressures of the slope. The other option is turf grass, which also forms an impermeable layer on the soil surface to protect the slope underneath. And drainage drainage channels must also be installed. And in the quarry land, as you've seen, the water drains naturally to the ocean, so the drainage channels would be the drainage channels will have to be directed towards the ocean. So in this case, after stabilizing with the stabilization measures in place and appropriate design, then we can say that excavating near a large water body, as we've seen, we would just be concerned by how far from the shoreline and how deep we can go because of the groundwater level, the sea level there, and also the permeability of the rock mass. And I can conclude that excavation in this case can be done at any depth and at any distance, as long as we have measures in place to take care of water inrush, which is the main challenge in this rock mass. And also the slopes have to be protected from the degrading impacts of water. And slope treatment needs to be concurrent with the excavation so that we remain with stable slopes as excavation continues. So in conclusion of chapter 7, we see that the overall slope angles for the north, central, and southern regions would do with 55 degrees, 46 degrees, and 41 degrees respectively. And for long-term stability, we can do with 53 degrees, 44 degrees, and 38 degrees. And the 10-meter bench height is recommended because it gives reasonable bench width. With the bench face angles of 62 degrees, we have 3.27 meters of bench width. At 53 degrees, we have 4.24 bench meters for the central region and 45 degrees bench face angle with 3 meters for the southern region. And the long root vegetation is proposed to use for slope stabilization. And excavation in this case, controlling water inrush into the quarry and also protecting the slopes includes drainage and application of geotextiles. So general conclusion of this research work, I would say that as currently designed, the quarry slopes are not in the best of shape for safe operations because the rock is weak and brittle, and the stability largely depends on the rock strength. And stability of the slopes is significantly affected by the presence of the karst hollows and made worse by the water seepage. Rainfall in this case poses the greatest challenge to slope stability. And the ocean water and groundwater inrush should also be taken care of when excavation goes below sea level and below groundwater table. The equivalent porous medium method that has been proposed seems to help in determining the failure modes that are likely to occur on the slope, with the smaller hollows contributing to planar failures, while the larger hollows could cause subsidence. And for strong rock, from medium strength rock of GSI 40 onwards, then the existence of small sized cast hollows might not be so significant in the modeling process. And it's important to maintain the stability of the slopes in this rock by applying measures to improve the rock shear strength and eliminate the pore pressures. I would recommend that further research looks into cast hollow shapes which were not considered in this case, and also to consider larger scale slopes for this method, because in this case we were limited by the machine's capacity to run a bulky model, and also seepage analysis could look into transient seepage. Furthermore, further research could also look at defining Moe-Coulomb and Hoch-Brown parameters for the root, the vegetation and soil mixture, so that we can quantify how much slopes are stabilized by vegetation roots. So finally, I would like to express my gratitude to everyone and the institutions that have contributed towards the success of this journey. First of all, to JICA, whose collaboration with my institution, JKU at back home, have enabled me to be here, and I'm grateful to Tissue University for hosting me and keeping me under the tutelage of my senseis, Professor Takashi Sasaoka, Professor Hideki Shimada, Professor Akihiro Hamanaka, and also the other member of the examining committee, Professor Kyonobu Kasama. So thank you very much for your guidance and contribution to this research work so far. I'm grateful to my colleagues in rock engineering lab and the other colleagues in other labs who contributed towards this work when we were consulting each other. I'm grateful to the Pingo Quarry team who enabled me to have a case study and also build data towards this work. And I'm grateful to my family members and friends who have contributed to keeping me sane during this journey. So this far, I would say thank you very much to everyone who's contributed to this work. Thank you very much.